So far in this series, we've looked at how you can use a camera or even an Xbox Kinect as a 3D scanner. But this is the 21st century and we're all walking around with advanced camera technology and sometimes additional specialist sensors just sat there in our pockets. So today we're going to be looking at a range of free mobile apps that you can use on your phone or tablet to convert them into a 3D scanner. So let's take a look. There's a wide range of technologies which can be used for 3D scanning, and we've already covered a lot of them in this series. We'll be looking at more of them later on in this series, and today we're going to be focusing on the ones that are commonly utilised by 3D scanning mobile apps. The first of these is photogrammetry. This is where you would take still photographs of the object that you want to scan, capturing it from every angle. You then run these photos through photogrammetry software which analyses them, identifying the same points on multiple different photos, and from that calculating how the images need to be folded for these points to fit together in 3D space, therefore creating the 3D geometry. Whilst, as I've just shown you, you can do this on your computer, there are some great photogrammetry apps out there like Reality Scan by the Unreal Engine developer Epic Games. Last week's episode was dedicated to photogrammetry, and so this method of 3D scanning was pretty well covered there. The difference is, in that episode, I was looking at photogrammetry done using any camera and then processing the photos on free software directly on my computer. By contrast, with these photogrammetry apps, you take the photos on your phone's camera and then upload them through the app to be processed server-side. Often this will either require a paid plan or will offer limited control or output quality compared to what you could achieve with software on your computer. Another couple of methods of 3D scanning commonly used in mobile scanning apps is NeRF and Gaussian or Gaussian splatting. NeRF, or neural radiance fields, and Gaussian splatting are both techniques that can be used to create 3D digital scenes out of 2D videos. NeRFs use a neural network to produce a volumetric 3D reconstruction, simulating density and calculating new angles by applying ray tracing technology to its neural network model trained on your input video. Gaussian splatting, which I may occasionally refer to as Gaussian splatting, uses a point cloud, similar to what we've seen in other forms of 3D scanning that we've already looked at in this series. Point clouds are collections of dots representing single points in space to represent relative locations and approximate colour of a surface. It then splats each point, effectively rendering it as a fuzzy sphere or a Gaussian, filling in the gaps between the points. Using this method, even a sparse point cloud could be used to generate an apparently solid model. Whilst NeRF by definition uses neural networks, the core component of most AI systems, Gaussian splatting doesn't inherently need AI. Gaussian splatting video to 3D apps and services, however, do almost always use AI or machine learning to optimize point cloud generation from the video and to optimize splat placement. Both of these methods can scan in what's referred to as 5D, which is the 3-axis of the object of the X, Y, and Z, and then the 2 dimensions of relative position from where it's being viewed from. As a result, they're able to scan objects with specular highlights and view-dependent textures because it takes into account how the appearance of a surface changes based on where you're looking at it from. We'll look at this more in a bit. The final method of app-based 3D scanning that we're talking about today is a little more device-specific. The past few generations of iPhone and iPad Pro have featured a built-in LiDAR sensor. LiDAR stands for light detection and ranging, and simply put, it works by sending out a laser and then measuring the time it takes for that laser to reflect off of an object and be received back by the sensor. Now, this method is referred to as time-of-flight depth sensing, and I'll be looking at this a bit more in next week's episode. But LiDAR has a little trick up its sleeve. Using either a phased array or a super quickly spinning mirror, it can send out lasers in multiple directions. Using this method, it can then detect and map an entire field of view from one perspective without even moving the sensor. Due to its speed and relatively low processing requirements, LiDAR is used in a wide variety of applications, from 3D scanning to robot vacuum cleaners and self-driving cars. Apple began adding LiDAR to their iOS devices around the time that augmented reality started being experimented with in mobile apps, and is likely the at least primary initial intended use case for it, for anything from making fun videos to visualizing how furniture would look in your home before you buy it. But it's also a really useful tool for 3D scanning, not just being fast, but also due to the way it works, it can scan things with relative dimensional accuracy. So if I was to scan these shelves right here, they've got roughly 33.5 centimeter gap between each shelf. If I was then to measure the space between the shelves in the scan, it would automatically show around 33.5 centimeters without me having to have manually scaled up or down the model to be the right size. Unlike the other two methods of 3D scanning mobile apps, which I've mentioned here, which require you to upload your scans to be processed server-side, most LiDAR apps will do all the processing on device. This is because Gaussian splatting and photogrammetry requires a lot of inference from the 2D images to figure out the actual geometry of the thing you've scanned, whereas LiDAR sensors provide pretty much all the raw data you actually need, so it doesn't so much require processing as just compiling it into a visual 3D model. As I already covered photogrammetry in last week's episode, and because these photogrammetry mobile apps are basically just a simpler version of that same process and with less control, I won't be looking more into photogrammetry apps in today's episode. So today I'll be specifically looking at 3D scanning mobile apps which either use a LiDAR sensor or provide video to 3D using NeRF and Gaussian splatting. There's a huge range of apps available for iOS devices that take advantage of that LiDAR sensor. However, some of them will require a paid subscription, whilst others are less focused on general 3D scanning and either are specifically for scanning, let's say, people, or for other purposes such as augmented reality or recording spatial video. Despite this, there are a few apps available that use the LiDAR specifically for 3D scanning, which don't require either a big one-off payment or a subscription to use. This episode isn't for comparing these apps with one another, although if you would like that, I can definitely do a comparison video between some of the better ones in a future video. Let me know in the comments. Today, I'll be using one creatively called 3D Scanner app, which is one of the more broadly capable of the free options available, and will be a good representative of iOS LiDAR scanning apps for this series. The LiDAR sensor is basically the reason I bought this iPad Pro rather than basically any other tablet. I thought it would be useful and just generally fun to be able to quickly, dimensionally accurately 3D scan things that I came across on my travels around the world as a wildlife cameraman. Frustratingly though, I bought this 2 shoots before my accident in Italy, which ultimately spelled the end of my ability to continue in that career, so I never really got to use it for that purpose. What I have personally found it useful for, however, is that I've scanned every room in my house and my garden, and thanks to its intrinsic dimensional accuracy, it means that if I ever wanted to buy, design or build something for my house, I can quickly load up the relevant scan and measure anything I want, even if I'm not at home. Now the 3D Scanner app is actually multifunctional. I'm using it today to represent the use of LiDAR in 3D scanning, but you could also use it for a range of other things, including photogrammetry. With LiDAR selected, the app has 2 modes. The first, normal, is basically point and shoot mode. There's just one button that allows you to start the scan, and then you click it again to end the scan, and then it will process it automatically. In this mode, as you scan, it will apply a wireframe mesh around anywhere that you've scanned, showing you roughly the geometry that you've captured. With LiDAR Advanced, however, you can select the depth of the scan, which is basically the maximum distance from the iPad that it will actively scan. This is great for being able to easily avoid scanning the background, as this will save you then having to delete it from the resulting model later on. In advanced mode, you can also set the resolution of the scan. You can set it to anything from 50mm down to 5mm, meaning that you can capture details as small as 5mm. Obviously, the higher the resolution, the better quality the output, but if you don't need it, especially if you're scanning something particularly large, a lower resolution will be quicker to process and produce a smaller file size to work with later. You can also set the confidence level, which is how confident it is in what it sees. A lower confidence level can help reduce geometry errors, but may also then require slower and more meticulous scanning. Finally, you can apply masking. With this turned on, you can select whether it's an object or a person, and then it will try and figure out what you're actually scanning and avoid scanning anything else. With the LiDAR Advanced mode, rather than applying a wireframe mesh to your scan in real time, like with normal mode, It applies more of a blobby mesh over the area that you've scanned to better represent what it's captured. I have found, however, that with both this and the wireframe overlay in normal mode, it seems to frequently either forget areas that you've definitely scanned, or just stop showing the overlay in certain areas, meaning you can't really rely on this for tracking what parts of the subject you've already scanned, and if anything, it's just a distraction.
It's so quick and easy to use even with larger items like this charity recycle bin.
Once you're done scanning, you can choose to either process it then, or if you want to get straight onto another scan, you can save it and process it later. When you do decide to process it, if you used LiDAR Advanced mode, you can choose the quality level of the scan, adjusting the level of geometric detail, if the model should be simplified at all, or whether or not a texture should be applied, and all of this will then affect how long the process takes. Whilst it's not immediate, the process doesn't take too long, just a few minutes at most, and once it's done, you'll then get this model that you can then look around and make some slight adjustments to. Once processed, you can then export your scan in a huge range of formats, and more importantly for us looking at 3D printing, this includes both OBJ and SCL, but I would suggest at this stage exporting in OBJ. Whilst this app does give you the tools to remove areas of your scan that you don't want, you're still going to need to close any cracks or holes and convert it into a solid object before you import it into your slicer and print. So once you've finished exporting, you're going to want to transfer this scan to a computer and then open it in a piece of software that you can perform some simple fixes with. A popular and free option for this, which I've already covered in this series, is Mesh Mixer. With your scan opened up in that, you can then close any cracks, delete any unwanted sections of your scan that you weren't able to remove with the app, and finally close any holes in the model by converting it to a solid. Then finally export it as an OBJ or STL ready to import into your slicer. Well, looking at the scan of the bin here in Bamboo Studio, it's definitely not perfect. There's a lot of flaws in it, but equally, it has captured the essence of the shape of this bin, and this was all from a scan that took just a few seconds. I'm not going to bother printing this because I don't want a print of a bin and the quality isn't really there anyway, but this is a good example of what the process can be up to this point. Well, that was a quick test with a large and fairly simple object, but how would it deal when spending more time scanning a slightly smaller object with much finer detail?
To find out, I've come back to Millennium Square that I visited in the photogrammetry episode to scan one of these statues again, this time using the LiDAR on an iPad.
It's certainly quicker and easier to use this LiDAR scanning app to scan this statue than when I scanned it with photogrammetry and had to take hundreds of individual photos. Well, that's definitely not the level of detail that I was hoping for. The LiDAR sensor in these iPads definitely has their limitations, with the smallest feature that they can capture in ideal situations being 5mm, so a lot of the details in this statue it just wouldn't have been able to capture even if it were under perfect conditions. I am quite surprised that it's managed to capture the rather thin book that the statue is carrying, but there isn't a huge amount of detail or nuance to this other than it being a relatively humanoid shape, and there are some holes here and there. The bottom of the feet seem to have not been picked up too well, so I'm going to have to cut off quite a bit of the bottom of the feet to give us a flat surface to print on, and then I'll probably add just a flat block at the bottom to manually add some flooring. I mentioned that there is a big range of LiDAR scanning apps available, but there is an even bigger range of mobile scanning apps that don't require a LiDAR equipped device. They just require an Android or iOS mobile or tablet with a standard 2D camera. There are loads out there, including Magiscan and Polycam, but today we'll be using Luma from Luma AI, which uses NeRF and Gaussian splatting for video to 3D. Luma AI may sound familiar, as I've talked about them before in my earlier videos on text to 3D AI generators, creating 3D models just based on the text prompt you enter. And they've more recently become even more famous from their Luma Dream Machine, which is a text to video generator, creating video from a text prompt you've entered. In one of those episodes, I used the Luma Create mobile scanner app to scan and then print Sea Gasket, and that turned out brilliantly. Let's see how Luma deals with scanning that same statue, and for this I'll just be using my phone. The user experience here is kind of like a hybrid between scanning this statue with photogrammetry and with the LiDAR app. It's much faster and easier than having to reposition and take separate photos hundreds of times like with photogrammetry. Whilst the LiDAR app tried unreliably to highlight what parts of the subject had already been scanned, with this there's no visualization. As a result, you need to try to remember what you've already scanned and make sure you cover every part from every angle. This is where employing a specific strategy, like doing complete rotations or orbits at a range of heights, can be really useful. But as I showed you earlier, the iPad overlay was unreliable at best, and really you'd need to remember manually anyway. One thing I would heavily recommend when using the Luma app is before you start scanning, go into the settings and turn on Save to Gallery. This will make sure that when you record a scan through the app, it also saves a copy of the video to your phone's gallery. I've had a few times where I've finished a scan and it's got stuck in the uploading or processing process, and there's no restart option. Unless you have the video saved to your phone, there's no option to try again. But with it saved to your phone, you can either just upload it through the app again, or you can upload it via the website on your computer. Once the scan is complete, uploaded and processed, you'll be able to view it and look around the scan on your phone or on your computer via the Luma website. When you load it up, Luma gives you this really nice transition, first loading the point cloud of the object, then introducing the surroundings, and finally flushing it out with a textured mesh. Whilst you can generate a link in-app to share an interactive version of your scan with others, for 3D printing you'll want to access your scan via the Luma Labs website on your computer. Head to lumalabs.ai/dashboard/captures. Browse to the scan that you want and then either click to view it, or you can directly download it. You can then choose the download type and the quality. High poly will give you the highest quality model. However, you may find that with particularly large or complex scans, choosing high poly will produce a model that your computer will struggle with. In which case, choosing mid poly should be more than good enough for most 3D prints.
Whilst exporting the object as an OBJ is the most straightforward option here for 3D printing, I actually found with this scan that when exporting as an OBJ, it seemed to assume that the lower legs and feet weren't part of the main object I was trying to scan, so it just cut them off. The only way I could find to get the entire model was to export the whole scene as a PLY and select full mesh. Then use a free online converter to convert the PLY to an OBJ. Finally then deleting the entire background in something like Mesh Mixer.
This one also needed the bottom of the feet cutting off and a flat surface adding for the base, but the feet were a little more complete than with the LiDAR one. And after all that, this is what we've got from each of them. The one from the LiDAR app has come out better than I was expecting when I was looking at it on the computer. There's obviously a person standing there holding a book or a tablet with one hand in his pocket, but there are some big issues. We're missing part of his head. Part of that might be down to me missing it in the scan, but then that could also be put down to the fact that the app was struggling to show me the areas that I'd already scanned. I'm pretty sure I did do several passes around the top of his head though, so that might be something else. We're obviously missing pretty much all detail and features and the bottom of his feet as well. By contrast, the one from the Luma app has significantly more detail to it. We can see a lot of features in his face, we can see his ears, we can even see some individual fingers that are holding the book, and on the whole there is more flushed out detail there, but it is still not ideal, but a lot more complete than what we got from the LiDAR one. At the end of this series, in the final episode, I'll be comparing all of the methods of 3D scanning that I cover in this series to see how they each perform in different tasks. This episode is specifically looking at mobile scanning apps and isn't intended for a comparison between them and other methods of 3D scanning. But because I've already scanned this same statue with photogrammetry in last week's episode, it's worth looking at what the differences are. Whilst with both the mobile apps, I had to cut off the bottom of their broken feet and then provide a flat surface for them to stand on. With the photogrammetry version, it was so complete that I just included part of the scanned floor and didn't have to cut anything off the statue itself. There's definitely a lot more detail in the photogrammetry one than either of these mobile app ones, but especially with the Luma one, the print has come out much better than I was expecting from how the digital model looked. Pretty much all methods of 3D scanning struggle with reflective and transparent surfaces. One common solution to this problem is to use 3D scanning spray, which applies a temporary matte finish to a surface. I'll be looking at this more in next week's episode. Nerf and Gaussian splatting, however, have a trick up their sleeve. They can be much better at dealing with reflective and transparent objects because they take into account how the luminance of a surface changes depending on the perspective you're looking from. As a quick example of this, pretty much the worst case scenario for scanning a reflective or transparent object would be a partially filled glass of water. So I scanned a partially filled glass of water with Luma, and this is how it came out. Clearly showing a solid object, not just representing the glass itself, but also understanding the volume of water inside the glass. By contrast, when scanning this with the LiDAR app, it doesn't really pick up the glass at all. Looking back at the statue, there's clearly a difference in quality between them, and Luma is definitely the better of the two if you're looking to 3D scan something to generate a detailed 3D model, especially for 3D printing. But if you want a dimensionally accurate scan, or if you want it to be processed entirely on device without the need for an internet connection, then LiDAR may be the way for you. It's worth noting that whilst the scans from the Luma app in this video have been okay, they've definitely not been great. But because of the nature of this video, where we're looking at specifically mobile scanning apps, the advantage of which is that you can take them anywhere, you've always got one with you, the subjects have, other than that glass of water, all been outdoors and with slightly reflective surfaces, which is not ideal for any 3D scanning method. However, as I mentioned earlier, in a previous video I have used the Luma app to scan sea gasket, a much smaller subject with fine details, and it was also indoors in controlled lighting, and the results from that were excellent. Again, as a comparison, this is the output I got when scanning sea gasket under the same conditions using the LiDAR 3D scanner app. Speaking more generally on 3D scanner mobile apps, whether it be LiDAR based or Gaussian splatting, the convenience of having it always in your pocket is one of the biggest advantages. And the convenience doesn't stop there. Even though Luma doesn't do on-device processing, neither of these apps require you to have a powerful computer when processing the scans. Other than general convenience, one of the biggest advantages of mobile 3D scanning apps, and specifically Nerf or Gaussian Splat, is their ability to be able to scan things that are transparent or reflective with relative reliability, something that even dedicated 3D scanners can really struggle with. Whilst LiDAR doesn't have that superpower, it can be really useful for being able to really quickly capture large objects with dimensional accuracy, being able to scan an entire room in just a couple of minutes. On the other hand, whilst you won't need a super powerful computer to process the scans from either of these apps, you will still need a computer to do some simple model repair and cleanup before printing. Luma requires an internet connection to upload the video for online processing. However, whilst LiDAR is probably the best option if you want an on-device processing 3D scanner mobile app, with the advancement of NPUs, neural processor units, I'd imagine it's only a matter of time before you can run things like Nerf and Gaussian splatting on a mobile device. As the primary focus of this series is to see the suitability of different methods of 3D scanning for use with 3D printing, in the final episode of this series, I'll be using Luma to represent 3D scanning mobile apps in my 3D scanning technology showdown. I hope you found this video interesting, and if you did, please do hit the like button to make my day. While you're down there, hit the subscribe and the bell buttons so you don't miss the rest of this series or my future videos and tutorials. If you really like this video and you'd like to support me and bag yourself some goodies, you can hit the join button to become a channel member, and among other things you'll get early access to my videos, exclusive access to the 3D Rev Discord community, a members discount at 3drevolutionstore.com, and you'll get a members discount on my limited edition 3D Rev build plate. For now, and as always, thanks very much everyone, and until next time, happy printing. If you're interested in seeing how Luma AI does generating a 3D model from a text prompt, I'll pop a link to one of my videos about that here. If next week's episode is already published by the time you watch this, that will be over here, but until then, that'll be the intro episode for this series where I cover a brief history of 3D scanning. Until next time, thanks very much everyone, and happy printing.